Hello student, good evening. Today we are going to learn definite integrals. In the previous session we have learned about indefinite integrals. So I would like to summarize briefly the previous concept of indefinite integration. So here if integral of fx is equals to capital Fx plus c, and we use integration constant in the case of indefinite integration, right? Here c is the integration constant, right? Okay. Then differentiating this result will bring us to the original, I mean initial function small fx, right? So when we differentiate capital Fx plus c, it is f dash x plus derivative of the constant c, and you know that derivative of any constant is 0. So ultimately it becomes capital F dash x plus capital F dash x only. And this capital F dash x is the initial function fx, I mean small fx, right? Okay. So basically integration and differentiation are two reverse procedures. Okay, and you are already familiar with the various formulas of how to calculate the indefinite integrals, right? So now let us look at definite integrals. So definite integrals are basically based on indefinite integrals, which are calculated between two different limits. One is lower limit and the other one is upper limit. So if the lower limit is a and upper limit is b, and the integrand is small fx dx, and if the indefinite integration of small fx is capital Fx plus c, then it can be written as like that. Okay, here a or b denoting the limits. Okay, so basically it denotes the difference of the values of the function at those limits. So at first we have to calculate for the upper limit and substitute x equals to b to find the function's value. So it will be this. And next we have to subtract the value of the function at the lower limit, which is f of a plus c, right? When we calculate this, the integration constant is becoming cancelled. So simply it will be like that. So in the next, when we will be calculating definite integral of any function, we simply omit the integration constant. Okay, we don't need all these things to write and calculate and cancelling. These don't need to be happen. Okay, so we will simply omit the integration constant in the next time. And you already know the various formulas of how to calculate independent integrals, and these are useful because independent integrals must be found out at first, and then we have to put the limits on it. So let us take an example how to calculate. So let the function be x square and the limits are 2 to 3. Okay, so when we calculate, we have to find out the indefinite integral of this function x squared dx equals to, we know we have to use the power rule. We have to use the power rule of integration, right? So the power rule says that indefinite integration of x to the power n is x to the power n plus 1 by n plus 1 plus c. So what will be for the function x squared? Here n is 2, right? So it is x to the power 2 plus 1 by 2 plus 1 plus c. Ultimately it becomes x cubed by 3 plus c. Now when we calculate definite integrals, we will not use that integration constant c. So we will simply write x cubed by 3, neglecting the integration constant because it is being cancelled. We have shown it previously, and the limits must be mentioned here. Now find the difference of the values of the function at those limits. So when we find the values of the function at x equal to 3, it becomes 3 cubed by 3, right? 3 cubed by 3. Okay. Then for the lower limit, it will be 2 cubed by 3. So ultimately, the value is 3 square minus 8 by 3. I mean, it is 27 minus 8 by 3, right? Equals to 19 by 3. So this is the way to find out definite integral. At first, there are two steps. At first, we have to find out indefinite integral of the given function. Next, we have to find the value of the function at the given limits and subtract. Then the result will be the value of the definite integral. Very simple. Okay. Now, let us understand, this is not the limitation of definite integration. This will not be bound in this concept. The concept is much wider because there is a very vital geometrical interpretation behind the definite integrals. Basically, definite integral can be used to find areas of a bounded region under a curve of a function. Okay, how is it going? Look at that. If the function is fx, then let the graph of fx be like that. Okay, so this is the graph of fx, the function y equals to fx, and let the interval is from a to b. Okay, so the bounded region becomes the shaded part here. Look at that. The shaded region is the bounded region, and this area can be found by calculating the definite integral fx dx from a to b. Simple as that. And this is a very powerful tool to find out find out area of various regions under a curve of a function. Okay, so I would like to give a brief interpretation. How is it working? Okay, how is it giving the value of as a definite integration? Okay, let us find out that the function fx is given here, and we would like to approximate the area of the bounded region at first by using rectangles, and you already know how to calculate the area of a rectangle, right? So let there be 3 rectangles, okay, of equal width h. All are h. Okay, all are h from the same interval a to b, and this function is y equals to fx. Okay, now let the rectangle height, the height of the rectangle be defined by the left endpoint of each rectangle. So here at x equals to a, the height of this first rectangle is f of a, because f of a is the height of the graph of fx, right? And the next one, I mean this second rectangle's height can be calculated by substituting x equals to a plus h. Notice that the value of x is increased by h, right? So the height of the second rectangle will be f of a plus h. F of a plus h. The second one will be f of a plus 2h. Now find the sum of the areas of those three rectangles. Okay, so the sum will be h into f of a plus h into f of a plus h plus h into f of a plus 2h. So this gives us the approximation of the area of this boundary region. But this is not giving us the exact value. We want exact value of the boundary region, because here, look at that. Here, these regions are left out to be calculated in the calculation of area. So this brings us error, right? This brings us, this is contributing to the error in calculation of area of the boundary region. So we need to make this error to 0. So we will take n sub intervals of equal length of h, okay, equal length of h, and we'll make that n approaching towards infinity. So ultimately there will be infinite rectangles of equal width h, okay, infinite rectangles. Let the nth, I mean last rectangle will be this, okay, and since we have already know how to calculate the height of the rectangles, we will calculate the sum. Notice that here the error of the area of the region is approaching towards 0. So it is ultimately giving the exact area of the bounded region. Okay, so let us find the sum at first. So for the first rectangle, it is h into f of a. For the second rectangle, it is h into f of a plus h. For the third rectangle, it is f of a plus 2h. And since we have n rectangles, and point to be noted that n tends to infinity, so ultimately the number of rectangles is approaching towards infinity, but we will consider n as an index. Okay, so n here denoting the last rectangle, so we know that the left endpoint of the last rectangle is x equals to a plus n minus 1 into h. Note that here the value of x starts from a, x equals to a, the next rectangle will be x equals to a plus h. So in this fashion, the left endpoint of the last rectangle, I mean nth rectangle, will be a plus n minus 1 into h. Very simple. So for the last rectangle's area, it will be f of a plus n minus 1 into h. Okay, now we have to write the limits also. And note that here the number of rectangles is n, and also we know that n is approaching towards infinity. So here b minus a is becoming n into h. Note that here the total width of all n rectangles is ultimately n into h, because there are n rectangles, right? And all of the rectangles have equal width of h, so it is nh, and this length is equal to the length of the given interval, which is from a to b, right? So b minus a equals to nh. So from this we can find that h equals to b minus a by n. Note that when n tends to infinity, h tends to 0. Okay, now we will take h as a common from the sum of each of terms, right? So it will be h into f of a plus f of a plus h up to the last term, f of a plus n minus 1 into h. Okay, now write the value of h in the form of n. So ultimately it will be b minus a by n into f of a plus f of a plus h plus up to the last term Okay, so by the fundamental theorem of calculus that says that the value of this sum is the definite integral from a to b integral of fx dx. Okay, so by this method we can find a boundary region under a functions graph between the functions graph and the x-axis on a given interval by finding the definite integral of that function within those limits. Okay, so in the next session we will discuss about various application of integration and also definite integration. And till then, keep learning and stay curious.